Hello everyone, this is Mike Dowding with the SD Mines Physics Department. Starting Chapter 10, which is the final chapter for the semester. And Chapter 10 is really going to be a culmination of all the materials that we've seen from all the other chapters. We're going to take the ideas of kinematics, force, energy, and we're going to apply all of those ideas to systems involving circular motion, or as we're going to start referring to it, angular motion. So far, the only thing that we've really had referring to circular motion has been centripetal acceleration, which we can define as the speed of the object at some radial distance r. And then if we apply mass to that expression, then we have an expression that tells us what the centripetal force acting on that mass is going to be. And that centripetal force was something that we had to identify in the system. It could be gravity, it could be tension, it could be a normal force, it could even be friction. But now we want to see if we can figure out how to describe the motion of an object that's going around in a circle without having to deal with constantly changing x and y components, because as we sorry, that should not have been a square there. As we continuously go around the circle, not only are we changing the direction of our velocity vector, but we're also changing the x and y values of our position as we go around that circle. Another thing that we want to consider is what happens to all of this information if we use smaller or larger radius values. And so to kind of get around all of that extra math, what we're going to do is we are going to define not so much where we are physically on the circle, rather we want to define where we are in terms of an angle. And so we are going to use theta to represent what we call the angular position. Now back in trig, traditionally you have this point right here, which we use as the 0 degree mark, and then as we go around a circle we can start measuring the angle with respect to that 0 point. Well, we're still going to use that 0 point, and if we want to, we could even label the angular position at that location. It would just be 0 degrees. But from there, if we move to some other point on the rim of the circle, that requires us to travel through a certain angular displacement. So we're starting here at 0, and we're going to displace through our angular values until we get to some final angular position. And so we're actually going to have subscripts for these. We're going to have our initial angular position, and we'll have a final angular position. except we're not going to use degrees anymore, unfortunately. In order to get this stuff to work out properly, we have to use radians for the value of our angles, and I'm going to explain in just a moment why that has to be. But for right now, we have initial and final angular positions, and anytime we have a final and an initial combination, we can put that together as a delta statement, and this would be the definition of our angular displacement. So maybe our final angular position was 60 degrees. And I know I just said we're not going to use degrees anymore, but I just want to drive home the point here as to what's happening. Initially, we started at 0 degrees. We ended up at 60 degrees, and so the angular displacement that we've gone through is 60 degrees. But like I said, we're going to have to start representing these in radians. And so if we go back to any circle, and we can either do this with a full circle or a half circle, but I'll just go ahead and use the full circle. For a full circle, we start at 0 degrees, we go all the way around, and that gets us to 360. But at the same time, if we start at 0, going a full circle means going 2 pi radians in terms of angle. And so 2 pi is equal to 360 degrees, or we can pare that down and we can say that for every 180 degrees we get pi radians. So what we want to do is take what we have for our angle and convert it to radians. Now I already have degrees on the top of our ratio here, so I need to eliminate the unit of degrees. I'm going to place the 180 in the bottom, and then the pi radians will go into the top. Now we multiply across the top and the bottom. We get 60 pi over 180, or pi over 3 radians. So that is our angular displacement. We started at 0 radians, and we ended up at pi over 3 radians. Difference in that is still pi over 3. Alright, well, let's talk about why we have to use radians. Now up here, I've got this other arrow, which is describing physically how far we have to travel along the rim of that circle. And that physical displacement along the rim of the circle is what we called arc length back in geometry. And arc length was represented as S. And so the physical distance, I'm going to make this a little bit bigger, the physical distance that we travel along the rim of any segment of the circle can be related to the radius of the circle and the angle that we have to sweep through. And that relationship is theta times r. And this equation can actually be supported by using the circumference equation that we're all too familiar with. the circumference of a circle is 2 pi r. And by circumference, that means we're going all the way around the circle. Well, by going all the way around the circle, your angle value is 2 pi. And your radius is your radius, and so the circumference is really just the arc length of the full circle. And in order for arc length to work, well, as we're very familiar, we have to use 2 pi, which is in radians, and we use that to get the circumference of a circle. And so by that same argument, we're going to have to use radians for all of the other angle measurements that we're going to use in Chapter 10. So prepare yourself to switch your calculators over to the radian mode, but then make sure that when you go to do your work for some other class that you switch the mode back. Otherwise you're going to be pulling your hair out trying to figure out why your trig functions and everything aren't evaluating properly. Alright, so we have our angular position, which is going to be represented by theta and measured with units of radians. We have angular displacement, which is just a change in angular position. And so that is also going to be measured in radians. But next we want to know how much time is this going to take? How long does it take to get from the initial to the final angular position? And for that, we will take our angular displacement and we will divide it by a time interval. And so what this means is that when we are at the initial angular position, there should be a corresponding time of t0. And when we get to the final angular position, there's a corresponding time of t final. And the difference between them is delta t. So this is our definition of angular velocity. And if you haven't picked up on it yet, angular is kind of the word of the day here. Really, we're just stepping through everything that we had the first day of the semester, where we were defining things like position, displacement, velocity, acceleration. Only now we're throwing the word angular in front of everything. Well, if you remember our discussions way back at the beginning of the semester, we brought up this idea of how big is delta t, because delta t could be a second, it could be a minute, it could be a couple of hours. The more time that goes by, the less and less accurate the measure of our velocity. And so the best that we can do by using a time interval of delta t, when I teach this at the beginning of the semester, I always tell my students that delta t is too big. In other words, anything greater than 0 is going to be too big for a delta t. And so the best we can hope for here is that we're going to get an average angular velocity. Now, I would like a way of denoting angular velocity. We used theta to measure angular position. So we're going to stick with the Greek letters. Otherwise, if I were to call this v, someone would definitely get that confused with regular linear velocity. So instead what we're going to use is omega, lowercase omega. This is our angular velocity, and as we said, it has to be an average, because until we know exactly how big or how small that time interval is, an average is the best that we can hope for. If we want an instantaneous angular velocity, then we need to shrink that time interval down to an instant. In other words, we need to bring delta t down to 0, and the only way to really do that is to let the calculus take over. And so if we had some kind of equation that described how our angular position was changing with respect to time, then we could take a derivative of that function and produce another function that tells us what the angular velocity would be. And I've just thrown some numbers together over here, but now we can step through this polynomial and we can take a derivative. And so what we would get here is 6t plus 4, and that would be a time-dependent expression for our instantaneous angular velocity. The units for angular velocity, we already have units of radians for the delta theta. Time is still going to be in seconds, and so we have radians per second for the units of angular velocity. And that leaves us with one more definition. What comes after velocity? Well, acceleration. But as we said, word of the day is angular. By definition, way back at the beginning of the semester, acceleration was the change in velocity with respect to time. But in this case, we're using angular, so we need a change in angular velocity with respect to time. Any delta can be represented as final minus initial. But again, if we're using delta t is too big. And so the best that we're going to be able to get is an average angular acceleration, unless we can bring this time interval down to something more instantaneous. So in that case, we would let the calculus take over again. And since we're sticking with the Greek alphabet, we're going to grab the Greek letter that most closely resembles an A, which is alpha. So here we have our average angular acceleration. If we want the instantaneous, then we need to have some kind of time-dependent function for the angular velocity so that we can take a derivative with respect to time. And well, right up here, we have just such a function. Let's take that function, let's hit that with a derivative, and produce a function for the angular acceleration. Well, when I take the derivative of omega with respect to t, all I get left is 6. And units of angular acceleration, we have radians per second for the angular velocity. We have seconds for time, and so radians per second squared will be the units for our angular acceleration. Alright, so now we have everything defined. We have position, displacement, velocity, acceleration, and if you notice, all the definitions that we used here are exactly the same as what we used at the beginning of the semester. The only thing that we've done is we've switched out meters for radians. Now what we want to do is we want to see, well, if that's the case, if all I've done is switched out units, how will the calculus be affected with these? And what we know so far is that if we take the change in angular position with respect to time, we get angular velocity. If we take the change in angular velocity with respect to time, we get angular acceleration. But where did omega come from? It came from the change in position with respect to time. And so that means we could also represent alpha as the second derivative of angular position with respect to time. And these are pretty much identical to the expressions that we had back at the beginning of the semester when we were defining regular displacement, velocity, and acceleration. And it was these equations that we used to derive the 5 kinematic equations. But because the structure of these equations is really no different, the calculus itself has not changed, which means that we can actually go through the math and we can derive 5 new kinematic equations using the new angular definitions. Except that we don't even have to do that. We don't have to go back and derive these new equations because all the definitions are the same, all the calculus is the same. All we've done is we've switched out regular position for angular position. We've switched out regular displacement for angular displacement. The only thing that's changed in any of these is the units. And so let's refresh our memories here as to what the 5 kinematic variables were. We had displacement, initial and final velocity, acceleration, and time. And this is what I like to call the missing column when I teach kinematics. Because for every kinematic equation, there are 5 variables, as we can see, but each equation only includes 4 of those. And each of the 5 equations is missing one of the 5 kinematic variables. And so what we have for the kinematic equations, this was one of them. And what is it missing? Well, it's missing displacement. It's missing delta x. And if we go through the list of all the other equations, all the other kinematic equations that were out there, and it'll take me a few seconds to jot all these down. So we should all be familiar with these equations. We've used them on and off all semester. And right now these equations are set up for a one-dimensional system, but we could just as easily upgrade these for 2D or 3D systems. All we'd have to do is put some arrow hats over all the vector terms. But now what we're going to do is we're going to take those 5 kinematic equations that we've already done all the work in deriving, And we're just going to rewrite them in terms of the angular variables. So anywhere in my kinematic equation where I had a delta x, I'm going to replace it with a delta theta. Anywhere where I had initial velocity, I'm going to have initial angular velocity. Anywhere where I had final velocity, I will now have final angular velocity. Anywhere where I had acceleration, I will have angular acceleration. And anywhere where we had time, we'll have time, because time is not going to have an angular equivalent. Time is just time. Okay, now comes the easy part. We're going to take the 5 kinematic equations that we had over here, and we're going to rewrite them. So first one, V final equals V initial plus AT. That becomes omega final equals omega initial plus AT. And what is that equation leaving out? Well, it's leaving out the angular position. So not only am I rewriting the kinematic equations, but I also have that missing column there to help me in identifying which equation I should be using for any given problem. The second equation will be rewritten as delta theta omega final t minus half alpha t squared. Third equation, delta theta omega initial t plus half alpha t squared. Next equation, delta theta half omega initial plus omega final times time. And then the last equation is omega final squared equals omega initial squared plus 2 alpha delta theta. And there we have our kinematic equations for angular motion. So anything that I have that's moving in a circle, we can represent the motion of that angular displacement using these kinematic equations. The number one rule that we had, however, for these kinematic equations, back when we were deriving the equations back in Chapter 2, we said that acceleration had to be constant. And so we're gonna stick with that idea over here, that the acceleration has to be constant. In other words, we're going to need alpha to be a constant. So what's next? Well, if you remember from your homework problems and your test problems, given any 3 of the kinematic values, you should be able to solve for the other 2. And so I'll just put some numbers up here. Let's say that we have a wheel that starts from rest, and it is going to accelerate at a rate of 2 radians per second squared. And I'd like to know how long it takes for that wheel to reach an angular velocity of 20 radians per second. So the idea was that given any 3 kinematic values, we can solve for the other 2. And here it looks like I only gave you 2. values, except keep in mind we said that the wheel starts from rest. So that means that we can use 0 for the initial angular velocity. And that's really all we need. I have 3 given values. I want to solve for the time. I'm going to come back up here and I'm going to grab the appropriate equation. So which one do we need? Well, we need the one that involves all 4 of these variables, or the equation that leaves out the one term that is not part of the problem. And so that makes it really easy for me to pick out which equation I need. It's the top one because it is missing angular displacement entirely. We need omega final equals omega initial plus alpha t. We are solving for time. Take a moment and rearrange your equation to solve for time. And then we will plug in our numbers. We have 20 minus 0 over 2 equals 10 seconds. So it will take 10 seconds for this wheel to come up to speed. Well, the next thing we may as well figure out is what is the other unknown in the system. So what is delta theta? So what is the angular displacement that this wheel has spun through? Now I have 4 pieces of information available to me, but there's only room for 4 pieces of information in any given equation, and this is the one that I have to solve for, which means I can only use 3 of the information above. And I am going to use what information was given to me because, you know, how do I know for sure that I solved the time correctly? Unless this is a problem on Wiley, and Wiley's going to show me the green after I hit submit, I don't know for sure. So I'm going to come back up and grab the equation that leaves out time, which is this one, to help me figure out what delta theta is. So that bottom equation needs to be rearranged to solve for theta. There we have it. We now plug in our numbers. We need 20 squared minus 0 squared over 2 times 2. And that's going to give us 400 over 4, or 100. And remember the units for theta are radians. So we have a angular displacement of 100 radians. Now, just out of curiosity, how many radians are there in one full circle? Well, one full circle would be one time around the circle, and so that would mean 2 pi radians. But 2 pi radians, if you plug that into your calculator, it's just a little bit over 6. So pi is your 3.14159, so on and so forth, times 2 gives us 6.2832. I'm going to end it right there. And yet we have an angular displacement of 100. So what does that mean? Well, it means that you have gone through multiple rotations or revolutions with this wheel. And so one of the ways that we can represent our angular displacement is in another unit that we call a revolution. So 1 revolution is equivalent to the angle that you would pass through when you go around in a circle 1 time. And so that angular value for 1 revolution is 2 pi. And this is going to be true regardless of the size of the wheel. If I go around the small wheel once, well, that's 2 pi radians. If I go around the big wheel once, that's also 2 pi radians. The difference between the two is the arc length. It is the radius that makes the big difference there. But both of these circles have the same angular displacement of 2 pi. So how many complete revolutions could we get out of this circle if 1 revolution is 6.283 radians? Well, we'll take the 100 radians that we had for our answer, and we will divide that by the 6.283, and we get just a little bit under 15.9, or excuse me, just a little under 16 revolutions. So almost 16 complete spins of the wheel. And if we can relate the change in angular position using complete revolutions, there's really nothing to stop us from continuing with that idea and measuring things like angular velocity in revolutions per second, or, as you may more commonly see in the real world, revolutions per minute. And this is usually pretty common with any kind of vehicle. You want to know how many times the wheels are spinning every minute, and most vehicles that are out there will probably still have some kind of an indicator dial that shows the RPMs with the vehicle. All right, so we now see how we can apply old information in the form of our definitions of position, velocity, acceleration, along with the calculus, and we have our 5 kinematic equations that have been updated for angular systems. And the rules for the kinematics are still the same. Given 3 pieces of information, we can solve for the other 2, with one exception. That exception being, what if you had a wheel that was spinning at a constant angular velocity of 5 radians per second? Well, a constant velocity implies 0 acceleration. If your velocity is not changing, then your acceleration has to be 0. And so what this would mean for this system is that both the initial and final angular velocities would be 5 radians per second, and alpha is 0. Well, there's your 3 values. So solve for the displacement and solve for the time. And here's where it gets interesting, because really what we're saying is you have a wheel that's spinning at a constant speed. How long did it spin? And if that doesn't really make sense, that's good, because we don't have enough information to answer that question just yet. The fact that we have initial and final velocities that are equal to each other really just means that we have one term, not two. And so two pieces of information, that is not enough to satisfy the conditions of a kinematics problem. And so we would need to have at least one more piece of information to solve a system like that. Now, before we end this video, there is one more thing that I want to comment on. And this goes back to the idea that the arc length, S, is related to our angular displacement and the size of the wheel. In all of our kinematic equations up here, you notice that the radius of the wheel does not show up anywhere in those expressions. And that's because it really shouldn't matter. We said right here that a small wheel that spins around in a circle of 2 pi radians, well, that angle is the same as a big wheel that spins around 2 pi radians. But what if we were to consider, let's take something like a meter stick. So our radius is 1 meter, but we're going to place some marks on that meter stick and just kind of sketch out the path that those marks are going to make as they go around the circle. The further out any of those points, the greater of a path that point has to sweep through. But every one of those points has to remain on that meter stick. So as the meter stick sweeps through the system, all 4 of those points are still in alignment with each other. Well, how can that possibly happen? The only way that that can happen is if the points on the outer radius are moving at a physical velocity that is faster than the points that are closer in. And this relates directly back to the idea of our arc length. Every one of these points on the meter stick has exactly the same angular displacement that they have to pass through. So theta is the same for all of the points, but because each point is at a slightly different radial value, each of those points is going to have a different physical distance that it has to travel. And thus the farther out on the meter stick, the further the distance that has to be traveled. But all of the points have to travel the same angular displacement in the same amount of time. So the only way that all 4 of those points can remain on the meter stick is if the points further out are traveling at a faster physical velocity. And the way that we can describe that physical velocity, because this was something that we started talking about back in chapter 4. This was how we related to centripetal acceleration. We needed to know how fast we were moving, and that's what v was measuring. Well, this is actually pretty straightforward, because on the left side of our equation we have the physical displacement along the rim of the circle, and on the right side we have our angular displacement. the one thing that is connecting the two of them is the radial value. Now we already know that if we take the derivative of angular position with respect to time, we will get angular velocity. Let's go ahead and keep the radius constant. And so what that means is first rule of algebra, what you do to one side you do to the other. Well, I've hit one side of the equation with a derivative, so I should hit the other side with the derivative as well. But here's the really interesting part. This whole time, S was the arc length. S was the value that measured the displacement along the rim of our circle. Now we're asking the question, how, oops, getting too far to the edge of the screen there, how fast do we pass through that displacement? In other words, what is the velocity at the rim of the circle? And so we now have an equation that allows us to switch not only from physical to angular displacement and back, but now we have a way of switching back and forth from physical to angular velocity and back. And this is actually the same velocity that we've been using for our centripetal motion problems. We need to know how fast our object is moving with respect to the tangent direction of the circle. In fact, we're going to stress that point by putting in a T right here to remind us, as we're going around in a circle, our velocity is tangent to that path. Well, let's take it one step further. If we can take a derivative once, what happens if we take a derivative twice? Again, I want to keep the radius constant, so we'll take the derivative of our angular velocity. That's going to turn it into angular acceleration. And so what we do to one side, we have to do to the other. And we said that we were calling this tangent velocity, so we'll keep with the notation there. Well, the change in velocity with respect to time is acceleration. But here comes the important part. If our velocity has been tangent to the path of the circle, then if this tangent velocity starts to speed up or slow down, the only way that that can happen is if we have some acceleration along the same direction. And so this is actually a brand new term. This is something that we have not seen before. We have seen centripetal acceleration, but when it comes to centripetal acceleration, which way does centripetal acceleration always point? And the definition of centripetal means center-seeking. Well, in this case, we have tangent acceleration. And so that means that we have to have an acceleration that is running tangent to the path of the circle. Well, that centripetal acceleration, we said that it was using the same velocity that we are now calling tangent velocity. Let's see what happens if we sneak in the expression of tangent velocity into the centripetal acceleration term. If we do that, we get omega squared r squared over r, but we'll lose that r and one of the r's in the top there. And now what we have is a system of equations that allows us to switch back and forth between the angular motion and the physical motion at any point on the circle. And so what this means for us is that we can go back to any point on our meter stick and we can say, all right, maybe this meter stick is spinning at a rate of 5 radians per second. What is the velocity of the point at the very end of the meter stick? And so we come down to our equation set here and we say, all right, our velocity tangent to the path of the circle is omega r. We know that we're traveling at a speed of 5 radians per second at a radial distance of 1 meter, because it's a meter stick. And so that means we have a value of 5. 5 what? Well, over here we've got linear measures, so this is going to be 5 meters per second. So any point along the far end of that meter stick has to be traveling at 5 meters per second as it goes around that circle. Same meter stick, same angular velocity, but how fast is one of the points halfway moving around the circle? So once again, we plug into our expression here. We have the same 5 radians per second, but we're only at a half a meter. And so we would have 2.5 meters per second for the velocity of a point that was only a half a meter out. Now, one final comment here. There is a little bit of hand waving that goes on with the unit analysis when converting from the linear values to the angular values and back. Everything on the right hand side should be in terms of meters per second or meters per second squared or just regular meters. Case in point, arc length should be in meters. Velocity should be meters per second. Both of our accelerations should be meters per second squared. But let's see what we have for units on the other side. For theta, we have radians per second. And for a radius, the length or the radius of the circle should also be measured in meters. And these two don't quite match up in terms of the units. On one side of the expression we have meters, on the other side we have radians per second times meters. So what do? Well, when switching from linear to angular, whoops, sorry, let's kind of jumping the gun here. We don't actually have seconds there yet. So down here we would have seconds, meters, radians per second squared, meters, So as we go through the units, we see that it almost looks like the radians have been thrown away in favor of the meters. And we've got one more combination here. We've got radians per second quantity squared times meters. So we have meters per second squared, radians squared, seconds squared times meters. So every time we transition from angular units to linear units, turns out what we have to do is we quite literally have to throw those radians out, because when it comes to physical measurements, the angle doesn't contribute any further. Whereas if we try to convert from a linear measure to an angular measure, we have to add the radians back in. So usually what I do when I'm teaching this in class is I tell my students, just take those radian units and put them in your back pocket, because at some point you're going to have to take them back out again and reintroduce them to the system. And I really can't provide a better description than that. What you have to remember is that those radians, or those pi values, that's really a ratio of the circumference of the circle to the diameter. And while circumference is 2 pi r, diameter is 2 r. And so what do we, oh, I messed that up. Sorry, pi. Here we go. Pi is the ratio of circumference to diameter. And so technically, pi should be unitless. It could be argued that. But we do give pi a unit of radians just so that we have something that we can measure as we go around in a circle. Alright, so that's where I'm going to leave off with this video. And with everything that we've covered here, we have essentially made our way through all of the definitions for Chapter 2. We've redefined all the terms. We've effectively used the calculus to define our new set of kinematic equations. We've also taken our knowledge of geometry with arc length, and we've come up with a very useful system that allows us to convert back and forth between the physical and angular values in a system. And so the next step would be to move on to Chapter 3 material to see how this angular stuff works in Chapter 3. But Chapter 3 was all about vectors. And vectors were all about having something with magnitude and direction. Well, think of it this way. As you travel through some angle theta, is there a magnitude associated with theta? In other words, is there some kind of numerical component? And the answer is yes. Is there a direction associated with your displacement? And This is the really nice thing about angular motion, is that you only have two choices. You can either rotate in the positive direction or the negative direction. So that's it. You can either rotate in the counterclockwise direction or the clockwise direction, and that's it. In other words, there are no components that we have to concern ourselves with when it comes to angular motion. And so that concludes the discussion on Chapter 3 material. We have our magnitude and direction for all of these angular components. As we displace, we either displace in the positive or negative direction. Our angular velocity will either be in the positive or the negative direction. Our acceleration will either be in the positive or the negative direction. Chapter 4 was our attempt to combine chapters 2 and 3. Well, we've already done chapter 2. We've already done chapter 3, which means we put them together, we're already done with chapter 4. So we have effectively gone through 3 chapters worth of physics material in one lecture. And so what we need to do next is we need to consider how all of this angular motion stuff is going to be represented in the other chapters. And as quickly as we were able to do 3 chapters in one video here, we're going to be able to do multiple discussions of chapters with angular motion in the next couple of videos that we do. So, see you then.